Hello, everyone. We're working through an introduction to statistical methods and data analysis by Ott and Longnecker. This is chapter 13, part 4, multiple regression, as well as model building and diagnostics. All right, so when we're looking at doing some model building, our first step is going to select all potential X variables that we may want to include in the model. And we want to first get familiar with our data. So we're going to understand the scientific problems and questions based on literature and previous studies. We're going to perform our exploratory data analysis, which includes plotting our data, as well as getting descriptive statistics. This exploratory data analysis helps us determine whether or not the relationship between X and Y is linear, whether or not there's colinearity, are there any outliers, is there any mistakes in our data, and so on. Step 2 will be to do our univariate analysis. This could be through simple linear regression or just looking at summaries. In step 3, we can create a model. This could be a full model. This could be a subset of the data based on best subset regression or stepwise regression, or based on previous literature. And in step 4, we're going to do model refinement, where we're going to decide on any transformations. We're going to check the residual plots, look at possible interactions. And then in step 5, we're going to look at model diagnostics by examining our residual plots and normal probability plots, and considering the effects of outlying and influential cases. All right. Another important piece that we've reviewed in the past is talking about colinearity. And the issue with colinearity is that when we interpret our beta hats, we're really saying, what's the effect of this variable while holding the other variables in the model constant? But if you have colinearity, once you change one variable, right, other variables are changing at the same time. And so the interpretation of the linear regression model no longer holds. So this interpretation becomes more and more difficult. So essentially, when you're checking for colinearity, remember that you're first going to fit a correlation matrix to your data, and then you're going to check your variance inflation factor. So with our data set of the latitude and longitude data set, we can create a new variable called new lat long, right? Which is really just the summation of the latitude plus the longitude. Now, in this case, we are purposely creating a variable that is collinear with the other variables. So let's check what happens with our correlation matrix. So if we look at the January temperature, right, this is our Y variable. And we look at the correlation between latitude, longitude, and new latitude, longitude. We see that latitude has the strongest correlation with January temperature. And one of the reasons for this is because if you remember from the plots in the previous videos, that both latitude and longitude didn't quite have a linear relationship with January temperature. Latitude actually had more of a parabola shape, and the longitude had a cubic shape. So we're not surprised that longitude has a weak correlation with January temperature, because this is testing the strength and direction of a linear relationship not a nonlinear relationship. But the second thing we're checking for is colinearity. So here we actually notice that nu lat long and longitude have a correlation above 0.9, right? So based on this, we can say that the variable nu lat long and longitude are highly collinear, which means do not have both of these variables in the same model. Okay, so essentially what we're going to do next is we're going to try to find a final model where we include only predictors that are significant, right? But some rules about that is that if you have the x squared in your model to be significant, we should still keep the main effect x. And if you have an interaction in the model, you should still keep each of the main effects for x1 and x2 if you're going to include an interaction of x1 and x2, regardless of significance. All right. So these are just some tips of what you should do for your model building, checking colinearity, fitting a final model, an example of issues with colinearity through a correlation matrix. Now we're going to talk about our variance inflation factor. All right. Remember from a previous video that the variance inflation factor, if your VIF for J is greater than 10, this will give you issues with your variance being inflated. Where this comes into play is on the significance of beta hat J. Remember that beta hat J really has a few different components for calculating the standard error. The first is S epsilon, right, which is the residual standard deviation. All right. Okay. The second is the sum of the x deviations, right? All right. So as the variability in xj increases, right? So as those xij's get further and further away from the x bar j's, right? Then that denominator is going to increase. If the denominator increases, that means that overall, your standard error is going to decrease. However, as r squared j increases, right, that's going to be getting closer and closer to 1. So the difference between 1 minus r squared j is going to be getting smaller and smaller as r squared j is increasing. And if the denominator is getting smaller and smaller, then that whole piece is going to get larger, right? So essentially, as your VIF increases, right, where VIF is 1 over 1 minus r squared j, as that increases, what's going to happen to your standard error, right? So as your VIF increases, your standard error is also going to get larger. So essentially your variance is going to be inflated. So it's going to be hard to tell whether or not things are significant or not, because essentially your predictor standard error is going to be inflated by this factor of how related your variables are. So if your VIF is equal to 1, you don't really have an issue with variance inflation. And your standard error for beta hat J, when VIF equals 1, becomes S epsilon over the square root of the summation of xij minus x bar j squared, right? But the standard error of beta hat j, right, when VIF is equal to 10, it's going to be 10 times S epsilon over the square root of xij minus x bar j squared. So all of a sudden your variance, your standard error is going to be very affected from having this variance inflation factor of 10. And now it's going to be much harder to determine accurately whether or not beta hat j is going to be different, or excuse me, whether or not beta j is going to be different than 0, because the variance has been inflated. So really the best thing to do in a model is to make sure that your variables don't have a high variance inflation factor, so that you can make good predictions about whether or not your predictors are significant. I hope you learned something today, and I'll see you next time.